Okay, so this week for the early morning lecture we looked at a couple of ideas in measures of location and measures of variation. First thing, we had a very quick look at the mean. So the idea here is I have some completely made up data points. They're all conveniently round numbers. Imagine this is my spend on drinks of coffee per day. So the idea is with this dot chart, there were 3 days on which I spent £2. There were 3 days on which I spent £9. There was 1 day on which I spent £6. Now, to calculate the mean, I add up, I find the sum of all these data points, and I divide by the size of the sample. And if I do that, I find that the sample mean is 5.2. And the little point we were making is that we can think of the sample mean as a pivot. If we imagine each of these as a pebble of the same mass, all balanced on a rod, the balance point for that rod would lie at the sample mean. Well, that's wonderful if you're doing mechanics or physics or something. Why are we looking at that? The idea is if one of these data points was shifted, it would be like having a leverage effect, and the mean would move quite dramatically just because one of those data points had changed. So here the sample mean has changed to 8.25. That's where we have to place the pivot point to balance these data points. And the point we were trying to make was that the mean is very sensitive to individual unusual data points. What does that mean for us? If we're analysing data, we need a good understanding of some really quite simple features of our data, and if we have these odd data points, we need to know about it. In this case, it's quite unlikely I spent £70 in a single day on coffee, so it sounds like there could well be some data recording error, and I might want to go and check my receipts and make sure I added them up correctly. It could be a genuine observation. Either way, it's a feature that I need to be aware of, and I will need to make adjustments about that later on. So that was the little point about the mean. It's very sensitive to small numbers of rather strange data points. The next thing we looked at is this thing called the 5-number summary. And the idea of the 5-number summary is we take a data set, we find the minimum value, we find the maximum value, and then we find the median. So sort all the data points in order, find the one that's in the middle, and if we find the point that's 25% of the way from the bottom when we sort them, this is called quartile 1, the 25th percentile. The point that's 75% of the way from the bottom when they're sorted, quartile 3, or the 75th percentile. And there's a way of visualizing these data points called the box and whiskers plot. We have a whisker telling us where the minimum value is, a whisker telling us where the maximum value is, and then the box is drawn around the data points that lie from quartile 1 to quartile 3. So here we have the 25th percentile, the point that lies a quarter of the way through the data set from the bottom. Here we have the point that is 75% of the way from the bottom, and the solid line is the median. There are two caveats about these box and whiskers plots. 50% of the data points lie within the box. Now the reason we have to be careful with this is it's visually misleading. When we construct histograms, we go to a lot of trouble to make sure that the area of the bars represent the proportion of points, proportion of data points. Here we have an area that is larger than here, but the way the box plot is constructed, there are the same number of data points here as there are here. The only difference these data points are spread out a little more than these data points, but there are still 25% of the data points here, 25% of the data points there, 50% of the data points lie in the box. So we really have to be a little bit cautious with these box and whiskers plots. Remember, what we're looking at is just the location of the 5-number summary. The second caveat, there are some slightly more technical presentations of the box and whiskers plot that might calculate, for instance, if you had a particularly unusual data point here and here, they wouldn't actually run the whisker to the maximum data point. They'd have a way, there'd be an algorithmic way of deciding this is an outlier, so I will draw the top whisker here and just denote that you have a couple of strange points there. You'll see that when we use them. If they have this visual miscue, why not just use a histogram? And that's a good question for this data set. But of course, what you can do with box and whiskers plots is compare several data sets side by side. So I could, if I had two data sets, I could have two box and whiskers plots and I could compare the two summaries. I could see that the range from the top to the bottom is the same, the size of the width of the boxes is the same, and the medians seem to be in the same relative position, but this data set is shifted upwards. And again, we'll look more at that when we visit these things in tutorials. So there's just a couple of ideas about visually summarizing data sets. Last week we also looked at frequency tables and histograms. What we want to do next is revise some formal definitions of variance. And following on from the 5-number summary, there are two very common methods of summarizing variance. Here is now the 5-number summary from the previous box plot written out in numbers. And one measure we could use is called the range. And the idea of the range is we take the maximum value and subtract the minimum value, and it tells us how far apart these two things are. And if we do that, we take the largest value 9, subtract 2, and we find that the range is 7. The other thing we can do is take the so-called interquartile range. So what's the distance between the third quartile and the first quartile? So how wide apart are our middle 50% of data points? And to do that, we take 6.5, subtract 3, and we find that the interquartile range is 3.5. The advantage of using the interquartile range perhaps is that it's not susceptible to these single one-off odd data points. The range gives us an idea about the whole data spread, but maybe it's influenced by the possibility of these strange one-off data points. So there's two measures of variance we can get from the 5-number summary, but the more measure of variance is the sample variance, and we'll pick apart the formula that's used for the sample variance. The first thing is, notice that the common abbreviation for the variance is S squared. So it's a Roman letter S squared, and by convention that's telling us we're dealing with a sample variance. We have a divisor here, 1 over n minus 1. You will see different divisors used. Sometimes you see people take 1 over n. We'll pick up on that detail later. The next piece of notation is the so-called summation operator, and it's like a for loop in computing, and it's telling you for subscript I starting at 1 all the way through to n, repeat whatever you're told to do afterwards and add the results to the previous iteration. So we need to look at what we're being told to do, and what we're being told to do here is take the data point x subscript I. So we have a whole set of data points we call x, we identify the data points like we do rugby players by numbers. So x subscript 1, x subscript 2, x subscript 3, and so on, all the way through to x subscript n. And each time we take the data point and we subtract this number, x, with a line over it, and we call that x bar, and that tells us the sample mean, again by conventional notation. So again, it's a lowercase Roman letter, but it has a bar above it. So what this algorithm's telling us to do, take a data point, subtract the sample mean, and then finally the last little point is that we square it. And if we set that out for a couple of the numbers in notation, we take the data point 3, the first data point, the sample mean is 5, so we subtract 5 from the data point and we get -2, and then we square the result and get 4. Takes the next data point, which was 4, subtract 5 to get -1, and then, as it's telling us here, we square it to get 1. Then the summation operator is telling us to add all these numbers together. When we do that, we get 90. And then the final step in calculating the variance is that we divide the 90 by 10 minus 1. There were 10 data points, 1 over 10 minus 1, 1 over 9, or divide by 90. So our estimate of the variance, the sample variance, is estimated as 10. So that's one take on calculating the sample variance. The sample is not a useful number in terms of interpretation. The data I gave there, I made up the story that it was spend in pounds. So of course the units of the variance are pounds squared. So the variance is some quantity that's measured in terms of pounds squared. I've no idea what a pound squared is. So for a whole load of reasons, it's much easier to work with the square root of the variance. So here, notice the conventional symbol is S. I take the square root of the sample variance, and if I do that, I get this number 3.16 pounds. And this is something we call the sample standard deviation. We'll find the standard deviations a very useful measure in lots of ways. Here's another way of thinking about the variance though. Instead of thinking about the arithmetic behind it, I've simplified my data set now. There are just 3 data points which we've indicated with these solid black dots, and I've drawn the sample mean with an X marks the spot. And if you look at what we're doing, I'm drawing a square box that represents the square of the distance between a data point and the sample mean. So I take the distance between the sample mean and the point and draw it into a square. I do the same for this data set. There's a square that represents the square of the distance between the data point and the mean, and I have a box here that depicts the distance between the square of the distance between a data point and the mean. And the idea of the variance is we add these areas together and, roughly speaking, take the average of those. So we add the area of these, and the formula I gave you, you divide by 1 less, you divide by 2, but it gives us some standardized measure of these squared distances. And of course you can see the problem with the sample variance, like the mean. If you have a strange data point, it's going to have, oops, that's really not well drawn. If you have a squared data point, it's going to have a very large, a very different data point is going to have a very large square that it contributes to the variance. So again, when using the mean and when using the variance, we have to be very careful that we've looked to see what our data set contains. So, just a caveat with using the variance and the mean, they are very susceptible to odd data points, and sometimes we call those data points outliers if you like using jargon. And a big part of the reason for doing visual data checking is just to see if there are these odd data points. What we do with it is a different story altogether, but in the first case we need to know they're there. Why use them? Why not just use the 5-number summary every time? The reason we use the sample variance, when it's appropriate to do so, we can use the sample mean and the sample variance as estimates of these abstract things called the population mean and the population variance. And the beauty of doing that, if this is appropriate, we have a probability model that has a generalizability or an applicability beyond our particular data set. And if we can do that, that's very, very powerful, as we'll find out.